tendency from Gunn High School in Palo, California. My name is Quinn.
My name is Ibrahim.
And my name is John. And today we will present to you our final presentation for the SMART competition, in which we will build sustaining infrastructure.
To build experience in the green energy field, we decided to join a competition. Because many of us have done previous math and science competitions, we have learned a lot of math and science from these competitions. So we decided to apply this to the green energy field, and we looked around and we found the SMART competition. So the basic premise of the SMART competition is that we are given a virtual gym, and we have to modify the gym so that it maximizes energy efficiency and decreases energy usage. More specifically, the three main goals we had in this competition were to reduce energy usage, reduce set points not met, focused a lot on the energy cost, especially because we realized that schools care a lot about how much we're spending for that energy.
We also thought that it's really important to focus on set point hours not met and economic costs, because we want to show that a sustainable building can be comfortable and be economically competitive, because that's one of the major counter arguments for these types of buildings. So that was really important to us.
So now we begin to look at our baseline energy audit. And here we have is just the first thing goal we're looking at, and this is the total energy use of the site. So here we have is the initial total on top, and here are a couple graphs that break down the energy usage. So on the top left, you can see an electricity breakdown in this building. It's a very simple building. We only have HVAC and lighting. And of course, you can see HVAC takes up maybe around 70% of the energy usage. If you look on the second graph down on the bottom, HVAC breakdown, you can see cooling actually takes up a majority of the HVAC, and that is probably due to the fact that cooling is usually on throughout the year, while heating is only on during certain points of the year like the winter. On the top right, there's a specific energy breakdown with the four things that were turned on in the building. And on the bottom right, we have a maximum energy consumption graph. And you can see here that while this may be contrary to popular belief, cooling and heating are actually, they have a much higher maximum energy than interior lighting. And because of this, we want to, we focus a lot on the HVAC system throughout the competition to improve efficiency in energy.
So on to the second point that we wanted to do, which was set point hours not met. And basically what set points are is they're a range of temperature in which humans are comfortable in, and we want to stay in that range. And in the beginning, the set point hours were not being met, were pretty high, so we definitely wanted to lower that as the competition went on.
And the final aspect that we looked for in this competition was to reduce energy cost and economics. So we decided to run a simulation to figure out the baseline energy cost of the building without any modifications. And this is a graph of the energy cost per month. And as you can notice, during the summer and winter months, the energy cost is the highest, mainly due to during the winter we need more heating to keep the building warmer, and during the summer we need cooling to keep the building cool.
So now we embark on a journey to modify the actual building. So a few of the things that we looked at mostly were, we started out with materials, and we moved on to HVAC, which if some of you don't know is heating, ventilation, and air conditioning. And then we move on to building orientation, roof window shading options, and power generation systems. So we looked at all five of these aspects throughout the competition. And here we begin, starting with our first is materials.
So with materials, the main thing we looked at was insulation. And what basically insulation is, the higher the insulation, the more the material reduces heat loss or gain from the environment. And we talked about this with our mentor, and higher insulation is not necessarily always better. For example, in a gym with a lot of sweaty bodies, if the heat is contained in, you're just going to have to use more cooling. So we want to find that perfect balance of insulation. So there are a number of factors we looked at in our materials to optimize energy efficiency. The first was zone. There are a total of 8 zones. Raleigh, which is where our building is located, was in zone 4, so we went with that. Then there was also the year, which was there were 3 options for year: 2004, 2007, and also 2010. 2010 had the strictest R value, which is stands for insulation, so we went with that. And also there was 3 options for residential, non-residential, and semi-heated. Residential also had the strictest R value, so we went with that. We also had these are the materials we chose. They go along with what I just said before. Zone 4 for all of them, most of them shown in 2010 were the selection. So these are graphs, and they really clearly display that we had a positive impact in all 3 areas. We can see from these graphs that we reduced the energy consumption of the building by 6.2%. We reduced the set point hours not met by 33.9%, and we reduced the total cost by 11.9%. So we see positive impact in all 3 areas. So that was very good.
The other aspect of the building that we changed was the HVAC system. So after we ran a simulation on the baseline HVAC system, which the basic HVAC, the default HVAC system is a PTEC air-cooled electric. We found that that system was not very energy efficient. Instead, we found that the water source heat pump was the most energy efficient. And this makes sense based on the basic idea of the water source heat pump. It works by pumping water through the building through a closed loop, and the water runs through a central cooling tower or boiler to change the internal building temperature. So the water source heat pump is more efficient because the water itself is only heated or cooled in one location, as opposed to the PTEC air-cooled electric, which requires that each small room be individually heated or cooled. And next, we ran some simulations to find just how energy efficient the water source heat pump was compared to the default PTEC air-cooled electric. And in total site energy consumption, we found that solely changing the HVAC system from the default PTEC air-cooled electric to the water source heat pump, we reduced the energy consumption by 63.8%, which is enormous change. We also reduced the total set points not met to completely zero, which is effectively 100% lower than the baseline. And costs were reduced by 70.6% as a result of the change.
So now we look at building orientation, and we did many simulations throughout to check out different kinds of degrees. And shown here, you can see 0 degree versus 45 degree. You can see that we first ran the energy simulation for a whole year, and you can see 45 degrees uses more energy than 0 degrees significantly. And on the bottom are solar exposure graphs. You can see 0 degrees has a much more maximum solar exposure compared to 45 degrees. And we also compared many other angles, but we just ended up deciding that 0 degrees happens to be just a pretty optimal building orientation with the roof point itself. And then next, we looked at the roof and window shading. And we decided on the one sloped roof and the second shading option. And here shown, you can see at 2 different times, the summer solstice and the winter solstice. And what we saw here is that during both times of the year, the roof is fully exposed. It has a maximum solar exposure throughout the year. And if you look at the window shading there, you can see during the summer, it's very minimal solar exposure, which is what we want during the summer, as we don't want as much solar exposure going through the windows. And during the winter, it's pretty much the opposite, where we have a much higher solar exposure. And that's good because during the winter, we do actually want more solar exposure through the windows. And here we have a roof comparison of all 4 given roofs. And you can see the flat, two-sided overhang. And then we just decided on the one slope roof for a couple of reasons. First of all, it does have the maximum solar exposure compared to the other 3 different roofs. And second of all, we wanted to add solar panels on roofs. And roof 4 was the most effective and efficient way, as it had the maximum maximum roof area for us. There's no two-sided things where it'll be harder and we'll lose some solar exposure for solar panels on the roof. And through these 2, we decided on roof 4 as our optimal roof. And in our shading comparison, also look shading 1 to shading 2. Shading 2 is much more effective in blocking the sunlight. And through this roof and window shade, this is pretty much application of passive solar heating, where during the summer, the sun is higher up in the sky, and there's not going to be as much sun penetrating through the windows. While during the winter, the sun is lower, and it'll be able to go through the windows, which is what we want.
So before we showed you the energy savings and the different increases in energy efficiency as a result of individual changes in materials, HVAC system and the roof angle and shape. But now we decided to combine all of these changes and run a final simulation to find just how effective our changes are. So we found that they were very effective. Starting with total site energy consumption, we reduced the total site energy consumption from the baseline by 70.0%. Total set point not met stayed 0, which is good, didn't increase. And the cost was reduced by 82.5%, which will save a lot of money for schools if they were to apply this green design in their gym.
So next we go on to power generation, as you can see from our beautiful solar panel picture on the right. We know solar panels are very efficient and very effective, and because of this, this is why many schools and many buildings use solar panels. It's very easy to install. As you can see, renewable, sustainable, eco-friendly. It's very abundant to find. It's also very silent. Obviously reduces costs right away after installation, and it's also very low maintenance, which are all major factors why many schools have solar panels now on the roofs and in the parking lots. So we used an online PV watts calculator to see how much energy we could generate from using solar panels. So we took the roof area and roof tilt angle, we applied it into the calculator. We gave it the weather location, which is Raleigh Durham International, and we chose which solar panel we wanted, and it happened to be the most efficient solar panel. And you can see here that we generated about 850,000 kilowatts, and that is pretty impressive, I think. And our conclusions is that we had a lot of surplus energy. Our solar panels generated way much energy than our building actually used, which happened to be 150 kilowatts, 150,000 kilowatts if we change it from church thermal units. And this is more than net zero. And we plan to use the smart grid to take the surplus energy and use it for the other surrounding things like train station or an airport. And another thing we want to conclude is that the building had no plug loads, and based on our dashboard, plug loads is actually one of the major vampire loads out there. And there was very limited electricity use as it's a virtual building. But all in all, we believe that our design is efficient, effective, and eco-friendly through our changes in the HVAC, materials, roof shading, and solar panels.
So our group actually took a lot away from the SMART competition. The process we used for the SMART competition, as we explained before, was we first established the baseline, and then we went around pinpointing the weaknesses, the problematic areas in our building, which was cooling. And then after that, we made changes such as material modifications, HVAC modifications, changed the orientation, and ran simulations to see if those changes had positive impacts. And that process is largely the same process that we're using in our energy dashboard at our school. So basically what our energy dashboard is it monitors the energy usage at our math and science building at our school. And basically what we're doing there is very similar to the SMART competition. We're first establishing baseline, which is before any modifications. Then after that, we run energy audits and see where the problematic areas are. And then we are in the process of talking to our school district and implementing changes to reduce energy consumption from plug loads. And then we're going to go back to the energy dashboard and see the positive impacts that we made. So the SMART competition actually had a very positive carryover to the projects that we're doing at our school. So we were also researching some other things that we can implement in our building. One of them was the smart grid. Basically, the smart grid computerizes the electricity grid, and you plant sensors on the devices around your building. And these sensors gather information and they send it back to the computerized electricity grid. And then from there, the computerized electricity grid can adjust the devices accordingly. For example, if the temperature is too hot and the air conditioning is not running high enough, the computerized electricity grid can automatically adjust these things, and that can save some energy. And we also research shielding air conditioning, and what that is you store water in underground tanks, and then you bring them to and during the night. And since night temperatures are cooler, you bring the water in through pipes in the building, and the air near the cool pipes sinks and the hotter air near the ground rises, and that results in a convection drip that passively cools the building.
And for the future, because our power generation systems, we only look at solar power. So we were thinking about looking at wind and water. And what we were thinking of is wind turbines and living roofs, as shown on the bottom there, the California County Science living roof. So we're thinking of, since we want to put solar panels on the top roof of the building, we have a lower roof on the first floor, and we could adapt a living roof on there, and it would prove to be economically efficient and energy efficient, as well as very architecturally attractive. And we hope to apply this to actual real-life buildings. And thank you to all the smart committee, battery systems, and our mental